All right, good, guys. You guys already got your note. You guys already have your guided notes. What's up here right now? You don't have to get, you know what I mean? Mr. Hager, can we get Liam a copy of the notes? You can get them for some reason. Oh, they're right here. All right, so we talked about this. Again, you don't have to write this down, guys. So we're going to talk about because the way Mr. Hager and I did this section last year, and years past, in a different book, they broke it down really nice. This book doesn't break it down as nice. So today, tomorrow, and on Thursday, all right, we're looking at stuff from 6.3 and 6.4. So today will be part 2. Tomorrow will be part 3, and then Thursday will be part 4 of it. All right? So we talked about this, right? What is the formula for exponential functions? We talked about it, right? We did this in the warm-up. Y equals a times b to the x. All right? Remember, a is going to be the value of, if we're looking at a chart, a is going to be the value of 0, the value of y when x is 0. All right? And then b is going to be what each y value is getting multiplied by. That's how we figured out if we're given a graph. All right? Yesterday, we had a couple situations when we looked at b, right? We had a couple like criteria. We saw functions yesterday where b was what? And between what range of numbers? Some of the functions we looked at yesterday. We looked at functions yesterday that had b greater than 1, right? Like the one we just graphed, in the warm-up was y equals 3 to the x, right? That little x variable, the exponent as x, all right? Whatever that's attached to, that's your b value. Whatever the little x is attached to, that's going to be your b value. Right? If the b is greater than 1, that's one criteria we looked at. All right? Another criteria that we looked at is when b was between 1 and 0. We want to talk about that a little bit more today. All right? I think we get to that too in the notes, Mr. Hager. What are you talking about here? Pretty sure. We have a whole page on that. Huh?
That's next week.
Oh, okay. I think we had a little bit maybe before that, or maybe after that. I know. I saw it on there because I put it on the notes. Huh? Oh, you did? Oh, okay. All right. So for the first one, right, guys? What we're saying, what that first thing says on your notes, where it says, hang on for a second, where it says this, where it says 0. Thanks, Natalie. So guys, what this is saying that A is between 0 and 1. Can somebody give me a number that's between 0 and 1?
1/2. No, that's not.
1/2, sure. 1/2. That's one thing. 1/3. What else? What's another thing that's between?
3/4.
Huh? 3/4. How about 0.36? What do you got?
No,
Oh, that was the first one, yeah. Say, where are those notes? All right, so what we're talking about here is a number that's between 0 and 1. It might be a fraction. It might be a decimal. As long as it's 0 point something. There can't be a 1 in front of the decimal point because then it's greater than 1. So if it's 0 point something or a fraction, as long as the number on the top is smaller than the number on the bottom. So on your notes, all right, where it says this, you're going to write, I want you to write, this actually compresses the graph.
Where are we writing that?
with the dot,
Right
here?
You can write it on the line right below the dot. Don't worry about filling in the dot.
Sounds good.
Yeah. All right. So all I want you to write is this actually compresses the graph. The stuff we looked at yesterday, right? What happened to the graph? We were comparing graphs. What was the phrase we used? It was a vertical what? What's happening to the graph? Stretched, right? We were kind of pulling them apart. Today when we look at them, they're going to be compressed. They're going to get tighter together, right? They're not going to spread out. They're going to get tighter. Like Mr. Hager showing us here, all right? And we'll be able to show it to you guys a little bit more when we do the examples. So Mr. Hager's graphing, right? The blue is 2 to the x, and the red is 1/2 x. So it's getting like a little bit tighter together. So, well, we're still going to write it. We're still going to write it by. We're still going to put. So when it says written like, we're still going to write vertical stretch by a factor of whatever a is. Whatever's in that a spot, right? Whatever comes before the number with the little x, whatever that is, all right? We're just going to put just like we did yesterday. Vertical stretch by a factor of whatever a is. So like Mr. Hager's putting on here, guys, the red graph is getting squished down, all right? It's compressing. We're pushing it together, all right? But we're still going to use the same phrase, vertical stretch by a factor of whatever's in the A spot, all right? Now, same rules as, I don't know if we're going to get to that today. Let me take a look. Now, if we have one where on your notes, it might say where it's negative, right? Where it says if A is, so it's same thing. If A is between 0 and 1, that's what we're saying. If A is between 0 and 1. Don't worry about writing that right in the sentence. All I'm worried about is where it says written like. For where if A is negative, all I'm worried about right now is where it says written like. So on your notes it says written like. We're still going to write it the same way, all right? Vertical stretch by a factor of whatever a.
Mr. Wood, I think we have that.
We have this?
Right here.
Yeah. We want to do if it's a negative too, right, Mr. Hager? We want to talk about that or no?
No.
But we do get one of the examples on the next page.
We did it, I mean, we already did it. But
Okay. Well, it's going to be the same thing, guys. Vertical stretch by a factor of whatever A is reflected over the x-axis. So big difference is whether it was the ones we looked at yesterday or the ones we look at today. If it's negative, make sure that the number in the A spot, if it's negative, you're going to have the 2 parts. You're still going to talk about the vertical stretch, and you also have to say that it's reflected. You could say flipped, you could say reflected. Do not put the factor of it, whatever A is. You don't put the negative part. You don't write, when we write these sentences, we never want to put negative. We know it's negative because it's getting reflected over the x-axis. So when you're writing these sentences, guys, ignore the negative sign. We don't care about that. We're not going to write that in our sentence. We don't need it. We're just going to write the positive number, and then by saying it's reflected, that takes care of the negative part. All right? So let's look at some, all right? So this is the original, that's the original function, right? Y equals 2 to the x. Our first one, y equals 3 times 2 to the x. All right? So, what number, before we even figure out what our sentence is going to be, what number is in that A spot? 3, yeah. So this is in the 3 is in the A spot. I'm sorry, Mr. Hager. 3 is in the A spot. All right? So is 3 between 0 and 1? Or is 3 greater than 1? 3 is greater than 1, right?
It doesn't really matter.
Doesn't really matter, we're still going to use the same sentence, right? What would we write for our sentence? What would it be? Is it going to have one part or two parts? One. How come? It's not negative, right? What would we write for our sentence? Good. Because it's a vertical stretch by a factor of whatever A is. A in this problem happens to be 3, and that function happens to be 3. Right, next one. One part, Vanessa, this next one. Is your sentence going to have one part or two parts?
First,
2 parts, why?
because it's negative.
Because it's negative. So vertical stretch by a factor of what?
Negative.
Careful. Remember what I said? We just talked about this when we were, before we went to this next page.
First.
What do you think, Ashley, what do you think? What would I put there for a factor? 3, right? We never want to put negative. So a vertical stretch by a factor of 3. Dominic, what's the second part of the sentence going to be? What does Mr. Hager need to type in? Say again? No. Because it's negative. Meaning? Flipped or reflected over the x-axis. Good. If you put flipped, that's fine too. If you put reflected and then in parentheses put flipped, that's fine too. As long as we know that's getting reflected. As long as we know that's getting flipped over. This part right here, this right here, handles the negative part. Let's look at the next one. Isolise, for this next one. One part or 2 parts? How come? Okay, what number's in the A spot? 1/3. So vertical stretch by a factor of 1/3. That's it, right? No reflected over the x-axis because it's not negative. It's really gonna get tight, right, Mr. Hager? Next one. Now we got quit it.
It's going to be vertical stretch by a factor of 1/3 reflected over the x-axis.
Perfect. Right, vertical stretch by a factor of 1/3 reflected over the x-axis. Very simple, guys. How many parts do you have if it's positive? 1. Vertical stretch by a factor of whatever. I don't care if it's between 0 and 1. I don't care if it's greater than 1. Use the same sentence. All right? We just want to show you guys that if it is less than 1, the graph is going to be a little bit tighter, but you don't have to graph them anyways. All right? And then if it's negative 2 parts, it'll be stretched and also flipped or reflected. All right? So on your notes, guys, I think we're on the back side now. So it says here, guys, in the function y equals a times b to the x. What's up, buddy? Oh, yeah, Mr. Hager, I usually have my original on top.
I need one.
Who needs one? Okay. Yeah, good, you guys be dancing around here. Oh, you this side. All right, so on your notes, guys. What does this say? A is what? No. Greater than 0 and what? So when A is greater than 0 and B is less than 1. This is called exponential, or B is greater than 1. So A greater than 0, B greater than 1. That's going to be exponential growth. That means your graph's going to go up in the positive direction. All right? The graph's going to go up in the positive direction. Does there'll be another type of exponential we'll talk about tomorrow. But today we're just going to talk about growth. All right? So that means when you graph it, it's going to look like this. Just like some of the ones we did yesterday. It's going to start off really shallow and then go up really, really fast. That's going to be your exponential growth. All right? Y equals, I'm going to put the little x here. Can somebody give me a function that would fit this criteria? A greater than 0 and B greater than 1. So I got y equals, what could be the first number I put in the y spot? Wait, Jordan? 2, that's fine. 2 is greater than 0. Put my little times.
1.5.
But B has to be greater than 1. You want 1.5 or 1.5? 1.5. That works too. You can do a decimal. 1.5. That fits the criteria for exponential growth. A is greater than 0. B is greater than 1. There you go. That works for exponential growth. All right. Let's look at. So when a quantity grows exponentially, so it's going up, right? It's going in a positive direction. It's increasing by the same percent over an equal amount of time. Like if I was looking at like you take on a loan or something. Like you get a certain, that percentage stays the same over time, so it's going to go up. Mr. David, do you want to do this part?
Sure. Or if you had an example like the population of a city
Yep.
is going up 2% every year, that's exponential growth of people in the city going up.
So we might, when we're doing this stuff, when we're doing this formula here, when we're looking at this formula here, guys, it's going to be a little bit, it's going to be a little different. It's going to be when we're doing this, it'll be like we're going to give you guys some word problems. But again, don't get freaked out. You don't have to tell me like 2 variables, right? It's just going to be plugging in numbers in the formula and so on.
So this example, or this problem, this formula shows you how to do exponential growth. Okay? If I want to compare it to the example I just gave, like let's say you had a city and it was going up 2% every year. You'd have to know how many people start in the city. You'd have to know what's the population when you start. Then you'd have to know how fast is the population growing. Okay? We call that the growth rate. If you're talking about money, like in a bank account, we usually call it the interest rate. Okay? Same idea. And then T is time. That's how many years have gone by. Do you want to know the population of the city after 5 years? Or do you want to know it after 70 years? Now, this formula assumes that R never changes. So if we say the population of the city is going up at 2%, it's going to go up at 2% forever. That's never going to change. Do you think that's realistic? Do you think that's realistic if we say that the population of a city is going to grow at exactly the same percent every single year? No, normally it changes. One year the population might grow at 1%, the next year it might grow at 3%, maybe the next year it actually drops 2%. Okay? Normally when you talk about growth, it changes all the time. But we're going to simplify it. Okay, so our growth rate will always stay the same. T is measured in years, in case I didn't say that.
Yeah, any problem we do, guys, T is always going to be years.
And R is your rate as a decimal. So if you had 12%, you can't use 12% in the formula. What's 12% as a decimal? 0.12. Yep. Or what about 7%? 0.07. All right? So we always have to change our percent to a decimal.
And guys, sometimes for like the time period in years, we might give you 1 year, and then we'll give you another year. But you're not going to put both of those years down. What would you have to do to figure out how much time's gone by? Subtract, right? Take the larger year, right, or the year that's more in the present, and subtract it by the year that's in the past. And that'll give you how much time's gone by.
Okay. Does everybody have the exponential growth formula? Okay. All right, so,
You guys have this written down in your notes.
this problem will be about a car. Okay, it's going to be about the value of a car and how it changes over time. So it says the owner bought the car in 1984, and the value of the car originally, back when he bought it in 1984, was $11,000. The value of the car is going up 6.9% every year. So it's changing. Okay, the value of the car is going up 6.9% every year. When a quantity grows exponentially, it's increasing by the same percent every year. That's exactly what's happening in this problem. Okay? So because the value of the car is going up the same percent every year, the value of the car is growing how?
What are we talking about, guys?
Exponentially, exactly.
Outside?
Okay? Sometimes values don't grow exponentially. Okay? If something grows in value exponentially, it means it becomes very valuable very quickly. Sometimes that happens, but not all the
It
time.
usually happens with cars, guys. Like the older a car is, usually depending on what type of model it is, usually it's worth more money as the time goes by. So obviously not as many, obviously not being made anymore. Not that many in that good a condition. That's why they're worth more money.
Okay, so part A says we're going to write a formula, using the one we just had on the other page, that tells me the value of the car over time. So how does the exponential growth formula start? Starts out what? Y equals.
Now remember, guys, this is not the one we used earlier. This is the model.
What comes after that? A, exactly, which is what in the growth formula? What did I call it? Yep. The initial amount, whether it's an initial amount of people, an initial amount of money. So look at this problem. What was the car initially worth? It was worth $11,000. That's in the spot where normally you would put A. Okay, the next thing you need is your growth rate. That's normally where you would put what letter? B. Okay, so right where B would go, we have to put the growth rate. How do you write the growth rate? So we need R, that's part of it,
Before that,
but something before that.
actually two things, a number and a sign.
1, start with that. What comes next? Plus. And now, how do we write the rate? Not 6.9. Remember, 6.9% is 0.069. Okay?
You gotta make sure you hit that percent with decimal.
One more thing I need. Not quite done. Yeah, T. And T is time. What can I simplify here? One thing I could do. What's in the parentheses? Yeah, how much is that? Yeah, 1.069. So this formula is exactly like the one you just learned. Y equals, that's A, that's B.
You guys, when we're doing these, it's really important that you this follow directions. You might do more than you need to. For this, all it asks you to do is just to write the formula. Not to solve, all right? Not to do anything but set up the formula. That's all you have to do. There's no arithmetic involved. You had to add a little bit, but that was it.
Does that fit the criteria for exponential growth? Yeah, what does A have to be exponential growth? But there's a criteria for it. It has to be,
It's gonna be
Josh? Yeah, definitely A is bigger than 0. What about the criteria for B? Bigger than 1. Is that bigger than 1? Just barely, but it is bigger than 1. Okay? So now we're going to use that formula. And there was an auction in 2004. We want to know the value of the car in 2004.
so now we have
What
to
year is it
solve.
now?
Well, that's the year that the car was sold.
No.
In this problem, it's 2004.
2004 right now.
Yep. So how do we figure out how many years have gone by? When was the car worth $11,000? What year was that?
1984.
1984. Okay, that's when the car had its original value. And now, the car is being sold in 2004.
That was like
So how many years have gone by? Jordan?
What?
How many years have gone by? Yeah. 20 years have gone by. Where do you think 20 is going to get plugged in this formula? For T. Okay? 20 years. So plug 20 in for T. So the value of the car 20 years later is the original amount times, what's in the parentheses? 1.069 to the 20. Okay, if we want to type this in, you can type it in all at once. Okay, the calculator will handle order of operations. Just type 11,000, press times. Now, in parentheses, I'm going to put 1.069.
Why can't?
Raised to what power? 20.
Why can't you just put the 11,000 right over against it?
You could. You don't. In this case, you don't need the time sign if you put the parentheses. You could do it like this on this calculator, and it would still work okay.
They can do it that way on their calculator too, right, Mr. Hager?
Yep.
It'd be fine. You know, but if you put time, like Mr. Hager did originally, times with the parentheses, it's still come out to the same thing.
oh my gosh.
So, what is the value of the car in 2004?
$41,771 and 11 cents.
92 cents.
Exactly. Why did you round like that? Why not round it to 0.918?
No, because
Because you always
it's
round
money,
to
so
hundreds.
you have.
It's money. We don't have thousands. We only can go to a penny, hundreds.
That's what,
You always round to the hundreds.
When you deal with money, exactly, always round to two places. And make sure you round properly. 5 or higher on that third digit,
Yeah.
round up. Right, so that's the value of the car, assuming that it goes up 6.9% every year. But again, that might not be true. Some years the car may drop in value for some reason. Or it may go up even more than that. Okay? So, any questions on that?
so guys, sometimes all we might ask you guys to do is just, based on what the problem says, just set up the function. Sometimes we may have you solve, depends on what the question is asking.
Now, what if I asked you, how much more is the car worth now than what it was 20 years ago? How would you figure that out? Subtract what? Yeah, if you take what the car is worth now minus what it was worth 20 years ago, you could figure out how much it's increased in value. So it's gone up like roughly $30,000 in value. A little more than $30,000. Okay, another example. You guys have seen this one. Okay, this is a problem we did probably within the first week of school, and then we did it again the week of the midterms. Okay? We talked about interest, okay, in a bank account. And people understand what that is, interest? So interest is, yeah, there's two kinds of interest. One kind is the kind that the bank pays you. It's kind of like saying thank you for putting your money in the bank. And the other kind is if you take a loan out, like to buy a house, you have to pay the bank interest. Right? We're going to look at the kind of interest that you, like, let's say you put money in a savings account and you check it a month later and you got a little bit more money in there. That's the interest. Okay? And I'm going to show you the formula for how interest works. Now, let's say you start out, just to make it simple, January. You put $100 in your bank account, and you don't touch it. You don't add anything to it, you don't take anything out. At the end of the month, you made $1 in interest. So when February starts, how much money would be in your bank account now?
You got interest on what?
If you made $1
If I made $1 every month,
in February, how much would you have?
so if you get $1 every month,
You get $1 in January,
So it'd be $101.
$101. So from January to February,
you got a whole dollar.
you got a whole $1. What was the amount of money you made? What was the amount of money you made interest on? What was the initial amount in your bank account?
100.
You had 100. Now you're going to make interest again during the month of February. But what's the initial amount?
Another dollar.
No.
Really?
What's the initial amount of money in your bank account now? 101. So now you're not just making interest on $100 anymore. You're making interest on 100. Plus you're going to make interest on the $1 they gave you last month. So now you might make a little more than $1. Maybe you make, no, not that much more. Maybe like $1.02. Or 3 cents.
Damn.
All right? How about when you start making interest in April? What's your initial amount now? $102.03. So each month you make interest on what you had originally, plus you make interest on the interest they gave you. So now you've got an extra $2.03. It's not a lot of interest, but it's a little bit.
A
So
little bit goes a long way.
after a while, it goes a long way. It does start to add up.
Isn't that how you end up in there?
If you are paying interest. Yep, there's that too. Okay, so here's your formula. It's very, very similar to the other one,
Add a few pieces.
but it's a little different. A is still an initial amount.
So guys, you have this on your note sheet.
R is your rate. And just like the last problem, how do you have to write the rate? Decimal. It's got to be a decimal. N is the number of times the interest is compounded. Does anybody know what that means?
How many times will you get interest?
Yeah, it's how many times the bank pays you a year. So in the problem I was just doing, they paid you every month.
Which is why.
So if interest was paid every month, how many times a year would you get interest? 12. So that means if you check your balance on January 1st, and then you check it again January 2nd, you're not going to have any interest yet. You check it January 10th, you're not going to have interest. You're not going to get your interest till the last day of January. Okay? So oftentimes when we look at problems, interest could be compounded monthly. What if it was compounded daily? On a normal year, how many times would they give you interest? 365, extremely small amounts every day. Yeah, it might be like a penny. So in that case, if a bank compounded your interest daily, you could log on, check your account at the end of every day, and you might see a really, really small amount more. If they only do it monthly, you have to wait till the end of the
Guys,
month.
that formula, guys, that formula's in a box on your note sheet. So you might want to fill that in. If you haven't already.
Okay, so N is the number of times it's compounded. T is the time you leave the money in your account. Let's say you leave it in your bank account for 5 years. T would be 5. Okay, like the last problem, what do you think I'm assuming about R, the rate? It's what? It's the same. Yeah, the rate is going to stay the same all year long. Okay, it's not going to change at all. Do you think that's true? Do you think that's something that normally happens?
Yes.
Interest rates on bank accounts stay the same all year long? No.
I think they probably go up.
Sometimes they go up, sometimes they go down. They change. Yeah, they could change every day. So that makes it a lot more complicated. Like, let's say your interest rate was like 1% for a week, and then it was 1.2%, and then it went.
Why would it go down? Why would it raise? Just like.
It has to do with the economy. It's pretty complicated why interest rates go up and down. But we're going to assume that it just stays the same. Okay, that makes it simple.
What's the interest rate right now?
The interest rate right now, it's extremely small. On like a savings account, it's probably like 1/10%. So basically, if you had $100 at the end of a month, you wouldn't even make $1. You might make 5 to 10 cents. Yeah. Interest rates used to be a lot better, but they're not really good on a savings account right now.
Wait, this is example 3, not 4.
Yeah, just put this, if you have to renumber it, that's fine.
I'm writing down my own notes.
Hey guys, you have this written on your notes, it's on there. You let everybody know.
I want to know.
But you have it on there.
All right, so example 4. Okay, you're putting $250 in a savings account. It earns 4% interest. How much will your investment be worth in 5 years? Aiden, tell me how to set that up.
How should I set it up? You should do numbers and then
What does it start out with?
250.
Let's go back and look at our formula. What's the first thing in that formula?
Initial amount / investment.
For that,
Why?
y equals. Okay, start with that.
Why is it equal to 250?
Next, put your initial amount, 250. Parenthesis. Yep. 1. Careful, 0.4 would be 40%. 0.04. What goes on the bottom of 0.04? What letter? Number of times interest is compounded. They didn't write it. Let's assume it's compounded monthly. So if the interest is compounded every month, how many times is it compounded a year? 12? Okay, Emily, what comes next?
You do the exponent.
Okay, what's going to be the exponent? What 2 letters?
Wait.
N and then T. N is 12. What's the T? How long are we leaving the money in the bank for? 5 years. Okay, this, I'm not going to type it all in at once. Okay. Let's start with what's inside the parentheses.
You have to multiply the two exponents outside the parentheses together.
We do have to multiply those as well. Yep,
Did you add them or multiply them together?
multiply them. What do I do first? What do I do first in parentheses? Antonio, what do I do first?
You do, you have to multiply the 12 into the numbers inside the parentheses.
Nope. That's not the first thing. PEMDAS, guys, PEMDAS, what's the first thing? And then we're in the
Oh, you
parentheses.
gotta add, then you do.
PEMDAS. Do your division first. Okay. 0.04. Divide by 12. Then what do I do with that?
You put it under and then you add 1 to that.
I have to add 1 to that. Okay. Round that to, let's go 1.0033. That's probably good enough. So if you're gonna round that number off, we should probably go to at least 4 decimal places. If you don't, it's gonna mess up our answer.
You need to multiply 12 times.
Now we multiply 12 and 5, which is what? 60. Now you can type all that in at once. Okay? If you try to type it all in at once in the first step, I think you're gonna make a mistake. Okay, how do I type that in? Somebody tell me, what do I press? 250.
Well, parentheses signs.
Parentheses.
1.0033, parentheses sign, and then your exponent.
And 60 is the exponent.
That's a big.
Okay, so if you leave $250 in the bank, that's what it'll be worth based on this problem in 5 years. So what would I round it to?
It'd just be 0.64.
It would be 304.64. How much money did we make in interest? How much money did we make in interest?
Look at what you started with.
It would be like $54.
$54 and
64 cents.
64 cents.
Hey, how'd you do it?
Got it.
I minus.
Yeah, subtracted, right? You subtracted the amount you got. Guys, listen. You subtracted the amount you got with the interest, right? 304.64 minus the original amount that you put in, 250. That's how we got $54.64.
So does this equation fit the criteria for exponential growth?
Yes.
Now, do you think, how much bigger than 1 is that number? Is it a lot bigger or a little bigger? Very little bigger. So even though this is exponential growth, it's kind of like this. It's going up so slowly. It's not like the amount of money you have is going to go up like that. Okay? It's going to go up extremely slowly.
Is there like somewhere like takes like a huge drop?
Take what?
Is there like one more like you need to
Guys,
show any
Guys, if I go back to this, guys, just real quick, listen. Guys, listen up. Instead of it being, if its interest is yearly, how many times? If it's yearly, if it's compounded yearly, how many times a year does it happen? One time, right? Okay, so I want you guys to keep that in mind for the homework. All right. Tonight, 6.3, 6.4. There will be on the backside some review of the stuff we did yesterday. Also, some of the stuff we did in the warm-up. Leave your notes out. You'll need them. We have 10 minutes left. We told you yesterday, this week is the last week of new stuff. So if you're teetering right on the edge of passing or failing, all right, you only have a few more days of stuff that's going to help you to pass. Last test of fourth quarter is on Friday. We have testing on Friday this week. You'll get the reference sheet for homework on Thursday that you can use on Friday. No class next academic Monday, so in a couple of weeks. We have no class. It's 4, 5, 6, 1, 2, 3 because of MCAS. All right, if you're in CP4 bio, you're taking MCAS biology. If you have CP2, then you won't take it until next year. Last thing. Just looking ahead so you guys understand. Your final exam is 2 weeks from this upcoming Friday, June 9th. All right? So next academic week, no class Monday. Tuesday, Wednesday, Thursday, those 3 days are all going to be review days. Mr. Hager and I are hoping that on Friday, we'll be able to give you guys the reference sheet so you can start working on that over Shop Week to get it started. It'll be just like the one we did for the midterm. You'll go back and look at your notes or on the YouTube website and find the examples and write them in. And then we'll practice on next week. All right? So that's it. While